Variable Study 2 revision video. I did this one for Galvanic cells, and I'll do it again because I liked it for revision, and maybe other people liked it, I'm not sure. Anyway, okay. Oops. Okay, so one of the more important things to know about this topic is the basics of collision theory. Collision theory states, for a reaction to occur, particles must 1. Collide, 2. Collide with enough energy to break the bonds of their reactants, and 3. They must collide with the correct orientation. Now, it's a bit hard to visualize this, seeing as molecules are quite a bit smaller than we can see, but if we look at the diagram here, well, it's more just a little drawing, but it doesn't really matter. If you look at it here, we can see the two dinitrogen oxides react to form a tetranitrate oxide. I don't think that's a real molecule now that I think about it. Well, it doesn't matter that much. So this hypothetical molecule, both of the oxygens have to bump into each other to form this. Now, say the nitrogen was to bump into the oxygen, there would likely not be a reaction. Or, if they didn't bump into each other fast enough, they wouldn't have enough energy to overcome the bonds, and there would also not be a reaction. A way to qualitatively analyze this is using Maxwell-Boltzmann curves, or distribution curves. For those of you who do methods, you'll see this sort of thing a lot later in the year, once we get to the standard the normal distribution, yes sir. What it essentially is a graph that shows us the amount of particles that have a particular amount of energy. So if I pick this point on the graph, we'll just say this is, I don't know, 25 meters per second, and this is 50 particles. So that means this point right here, there are 50 particles moving at 25 meters per second. Obviously, there's a large peak here, and as you gradually get higher, you get to more and more energy, less particles have that amount. So generally, the Maxwell-Boltzmann distribution curves will be biased to around here, but it depends on what temperature. Now, I don't want to spend a lot of time on this, considering Miss has said she probably won't be putting distribution curves on the test, but it is good to know a few things about it. For one, you can draw from a certain point on in this graph, the particles will have enough energy to react. So from this point on, if particles collide, they can react. But you can notice here, there's another one. The activation energy 2 is with a catalyst. Now, if you remember, catalysts actually lower the activation energy, which means less particles. Well, no, particles have to have less energy to react. So the shape of the curve doesn't change. The particles all have the same amount of energy. It's just that it takes less of it, so more of them are eligible for a reaction. There's another way to increase the amount of reactions that occur, and that is through increasing or not decreasing temperature. You can see on the red one, we'll just say this is being heated, where the black one is the normal, and the blue one has been cooled. In the black one, it's shown to be a lot more flat, which is to say the average energy of particles is a lot more. So if we just say this is the bound for activation energy, by far, red has the most. Then a little bit for black, and then a tiny bit for blue, which is cold. It's important to note, because the amount of particles don't change, the area under this graph doesn't change. It just gets flatter and more biased to either the low energy or high energy position, depending on whether or not you've heated it or cooled it. Okay, chances are we won't get a question on that, but it's good to know. Something we probably will get a question about is energy profiles. They're a weird kind of graph, but if you're familiar with them, it makes things a lot easier. So the x-axis is time, or sometimes you see it as progress of reaction. Sorry about the handwriting. So time or progress of reaction, and the y-axis is potential energy, which is to say the energy of the particles. In this example, we have an exothermic reaction. This peak here represents the activation energy, which is to say the amount of energy required for a reaction to occur. Please note, this is not part of the heat of reaction or heat of enthalpy, because it's released right after. This is just what's needed to kickstart it and to get it going. Heat of enthalpy is a different thing. It's this part over here. It's how much the enthalpy has changed by. In this case, this is an exothermic diagram, seeing as the energy of the reactants is greater than that of the particles. So the heat of enthalpy here would be negative, because it's all of this and it's going down. An interesting thing to note, the back reaction for any given reaction it has the same energy profile, just flipped. So this is the same height and stuff, but it's all just flipped. Sorry. Perhaps the most important thing to note here is that the activation energy also includes the heat of enthalpy, because it needs all this height to react. And once it does that, it keeps some of it. It keeps some of the energy. Of course, it also releases some back out, but it is a net gain of energy. And it is the mirror image of the exothermic one. Oops. Yeah. Now, another very important thing to know is how a catalyst looks on an energy profile diagram. We can see that the respective peaks for E of A1, which is to say activation energy 1, or uncatalyzed, it is higher than E of A2, which is activation energy with a catalyst. Because of this, E of A2 has a faster reaction rate. It completes the reaction faster, though it does stay at this point. It comes to the same final, energy level. Its activation energy is smaller, and it takes less time to complete. Now, one of the biggest parts of this unit is also manipulating collision theory to increase or decrease a reaction, or its reaction rate. Everything here will increase the reaction rate, but please note, if you do the opposite can happen, but it's a bit different for some things. Just be careful with it. So increasing the surface area to volume ratio increases the amount of collisions. If you think about it Stuff like, if you have, say, an apple, and you peel it, it'll brown on the edges, but if you cut it up, all of the slices get browned, which is to say, the surface area, more of it's exposed, so more of it oxidizes, because the browning is an oxidation reaction. When it's just in the lump, less of the surface area is exposed, there are less collisions, and hence less reactions. A temperature increase, now don't get this confused with the extent of a reaction, it heavily increases the amount of collisions and the amount of successful collisions. Now, the increase it has to successful collisions is greater than that. It's bigger than the effect that it has on collisions. So, the main thing it changes is when particles collide, it makes it more likely to be successful. It does increase the amount of collisions, but this is the big one. This is much more of how it helps. Another thing to note is concentration or pressure. They're sort of one and the same. You can think about them as the same thing in a lot of this unit. Seeing as, you find the concentration of a gas chamber by dividing the amount of mole by how large the chamber is, and you do the same with a solution by dividing the amount of mole by how much volume there is in the solution. If you increase the concentration, it means that the solution or chamber is a lot more populated, and particles are just a lot more likely to bump into each other. That also does increase temperature. Usually they like to be nice and dry. If something's added and pressure is kept and temperature is kept constant. Now catalysts don't do anything except for increase the amount of successful collisions. It doesn't increase the amount of collisions. It doesn't increase the extent of the reaction. It just increases the reaction rate. Catalysts are quite an important thing in industry and in the course as well. They increase the reaction rate by providing an alternative, lower energy reaction pathway. Below here is an experiment that we've done. This is esterification, or better known as, well, not better known, but more formally Fischer-Splier esterification. You can see, since we did it in an acidic solution, the hydrogen ion acts as the catalyst here. So that's why we had to add the sulfate, the sulfuric acid, because that gave this path, it allows this pathway. It's very complicated, you don't need to read it, it's good for illustrative purposes. The hydrogen ion allows all of this to occur. It's a lot lower energy pathway than if we didn't have the hydrogen, so the sulfuric acid is a catalyst. There's two kinds of catalysts, homogeneous and heterogeneous. A homogeneous catalyst is in the same state as what it's catalyzing, so you can say stuff like enzymes, since they are also usually aqueous, they're homologous, and heterogeneous ones are more stuff like metal plates used in ammonia production, because the metal plates are the solid and it's letting gases absorb onto the surface. It's not really important how it does it, but it's a solid that catalyzes a gas reaction, so it's heterogeneous. It's in a different state than what it's catalyzing. Alright, the extent of reaction is a fairly difficult to grasp concept. A lot of the time, the single arrow symbol doesn't really explain a reaction. In fact, most of the time, a reaction can also occur in reverse. So we write the double arrows. Be very careful with this on the stack. I doubt this is going to be as nice as she was last time with the double arrow situation. We don't want to lose a bunch of marks for nothing. The extent of reaction can be thought of as how much of a product is formed. Do not get this confused with the rate. The rate and extent are entirely different. There will be questions about both, and if you get them confused, you'll get it wrong. The extent is how much product is formed, or you can say the percentage yield of product. There's a few different ways to measure the extent, as with the rate, but the extent refers to how much of the product forms. The rate is how quickly the reaction occurs. Now, with the double arrows, we get to the concept of equilibria. In equilibrium, the backwards and forwards reactions are occurring at equal rates. Though a system in equilibrium may appear static, the reactions are still occurring. This is why we call it dynamic equilibrium. If you do have like a beaker of something or other, and you add, what did we use? I think it was iron thiocyanate, and I think it was just iron thiocyanate. If you just have a beaker full of that, and it decomposes, it makes that nice red color, you might look at it once it's reached a steady red color and think, oh, it's done reacting. It hasn't. It's just that the forwards and back reaction are occurring at equal rates. So while it looks static, it looks like the red ions have stopped forming, they're still being formed, just at the same rate they're decomposing. Hence, dynamic equilibria. So dynamic, it's still going, it's still fun, it's interesting. Maybe not fun or interesting, but it's moving nonetheless. Now, more on the position of equilibrium, it's essential to understand that K of C, or the equilibrium fraction, does not change unless temperature does. Position of equilibrium refers to the specific system's amount of products and reactants, or its yields, or there's a few different ways to say it. It really depends on what makes sense to you. That's not something I can tell you. Hopefully you already know by now, but understanding exactly what the position of equilibrium is very helpful to being able to word your questions and understand your answers. There is a way to qualitatively analyze the extent of reaction. We do it using this formula. All of this icky stuff where P is product, P of n is product indice, P1 of n. You should be very familiar with this by now. It's not a very hard thing to do. Just remember, when you want to write the units, you have to remember, replace all concentrations with just m, keep the indices, so just making up examples. So you multiply them, m to the 5, m to the 8, so it becomes m to the minus 3. So you get rid of concentrations, you rewrite it as m, and then you cancel out to find the units. In this case, just random numbers, it's m to the minus 3. Now this is called a reaction quotient. Q of C is the reaction quotient at any point in the reaction. There's a bit more, there's a more useful one, I find, which is K of C. K of C is defined as the reaction quotient when the reaction is at equilibrium. It's important to note, in any given reaction, doubling the coefficients, any reaction, sorry, I should write in equilibrium. It is important to note, in any given reaction, if it's in equilibrium, doubling coefficients squares K of C. Halving it, you square root K of C. Switching the products and reactants, you find the I think it's called conjugate, 1 over K of C. There's probably going to be a question on this sort of thing. It's important to remember how to manipulate K of C. Now, for the fun part, stoichiometry and equilibrium. In any given, so this is just an example question of, it helps us find how to, manipulate K of C and work around it with the concentrations. So, in any given solution of water, some self-ionization will occur when water forms hydroxide ions and hydronium ions. The equation for this is given. 2H2O goes into hydronium and hydroxide. At 25 degrees Celsius, the concentration of hydroxide hydronium ions is 1.003 times 10 to the negative 7, and H2O is 1, which is 1 mole per liter. Oh, yeah, that's not right. No, since water is a liquid, we just call it 1. If something's in a different state, we just say it's 1, because you can't really have the concentration of something that, isn't aqueous or isn't a gas. In this case, it's water liquid, so it's just 1. And K of C is 1 times 10 to the negative 14. So if we want to find OH minus, or the amount of hydroxide ions, we write the reaction quotient. So products over reactants. Remembering that there is a 2 here, so there's a 2 here as well. Say 1.003 times 10 to the negative 7. 1 times OH minus, minus goes on the inside, equals 1 times 10 to the negative 14. And then from the calculator, dividing this by this, we get 1.003 times 10 to the negative 7 mole per liter of hydroxide. If you remember back from last year when we did acids and bases, that's something we went over. It's pretty interesting, I think. I should have got my calculator before a second. Alright. So, if we have a 100 milliliter beaker of water at 25 degrees, it is found through a digital pH recorder, the new concentration of hydroxide ions is 2.005 times 10 to the negative 7. Find the new equilibrium quotient. So, for this, we use what's called an ICE table, which is initial change in equilibrium. There's 3 things we need to worry about. So we can say hydronium, hydroxide, and water. So initial is 1, Initial is 1.003 times 10 to the negative 7, and initial is also 1.03 times 10 to the negative 7. The change, hold on just a moment, I got this one wrong, because we first need to convert it all into amounts. So to do this, we have to divide it by 10, because it's 100 divided by 1 liter times 1.003 times 10 to the negative 7, which is to say 1.003 times 10 to the negative 8, 1.003 times 10 to the negative 8, and then 1. Okay, the change plus, no, we'll do it the proper way and find the amounts in the new place. 5 times 10 to the negative 7, 2.005 times 10 to the negative 8 mole, and then we have 1.003 minus 2.005 times 10 to the negative 8. It gives us, no, whoops, I did it the wrong way around, so it's supposed to be 2.005 minus 1.003 gives us 1.002 times 10 to the 8 mole. So plus 1.002 times 10 to the negative 8, 1.002 times 10 to the negative 8, and so the final concentration is 2.005 times 10 to the negative 8. No, not concentration, sorry, the final amount. That's 10 to the negative 8. Now, water isn't the best example, and I'm sort of sorry I used it, but seeing as it is in liquid, we'll just keep it as 1 the whole way through. I mean, this sort of change is really, really small, so we can't really recognize it, but it's important to know that it is there. I'll erase this for more room. So we are left with 2.005 times 10 to the negative 8. We're dividing it by 0.1, which gives us 2.005 times 10 to the negative 7. And that's our concentration of hydronium. We already know our concentration of hydroxide is this. So now we just have to plug it back into this formula and we'll find our answer, which is 2.05 times 2.05 to the negative 7 squared. Okay, which gives us, okay, I don't want to write it out, but you should at least write the formula that you're using. But this times this gives us 4.02 times 10 to the negative 14. We'll look at units, 1 here, 1 here, 2 here. So it's wait, no, if the units cancel out, you just don't write units. Okay. Now, my least favorite part of this topic, Le Chatelier's principle. It's probably the most boring part of it. It essentially means a change forced upon a system in equilibrium will be partially opposed by the system. This happens a lot. There's a lot of questions on it. One of the more obvious ones is pressure and concentration. So imagine this vessel of gas, and imagine I press down on it. So everything in here gets a lot closer together, which is to say the concentration I've made the concentration of this system much higher. Now, according to Le Chatelier's principle, we want the concentration to oppose this change, which is to say, to make the concentration lower. If we look at my scientific diagram of the reaction, 3 dots go into one snake. The system's going to want to make more snakes, because it doesn't care if it's snakes or circles, it just cares about the amount. So an increase in pressure will be opposed by making less particles. In this case, the system can do that by reducing the amount of the side with the more particles, and thus going the forwards reaction to make the ones where it has less particles. Now the opposite can happen as well. Let's just say I open the vessel up. So we have big vessel, lots of room for everything. I've actually diluted this solution, or not solution, this chamber quite a lot. This change will be opposed by undergoing the back reaction, which creates more particles. Now the system, it couldn't care less if it was a snake or if it was a circle, if it was a drink bottle, if it was a frog. It just wants more. So it doesn't care what the identity is, it just wants to return the concentration to be higher or lower, depending on whatever you've done to it. Oops, I wrote concentration twice. Just remember that the principles with gas are pretty much the same with concentration, except you do it through different ways. If you wanted to dilute something, you just add water instead of increasing the volume space. And if you wanted to concentrate it, you just evaporate off some of the water. Okay, this is probably the one that tricks people the most. Temperature. Temperature has a unique effect on a system in equilibria. The system will oppose it by undergoing a specific kind of reaction. It of course depends on the sign of delta H. So just say we have delta H and it's greater than 0, which is to say it's endothermic. So an endothermic forwards reaction. If I heat it, the forward reaction will occur to a greater extent because it wants to oppose the heating. And it can do this by doing the endothermic reaction, which takes in heat. So Le Chatelier's principle states, an increase in temperature for an endothermic system will accelerate the forward reaction because to oppose the change, the system needs to take in energy. Just say I cool it, it'll still want to oppose it, but this time it has to go the back reaction, which in this case would be exothermic. Pardon me. So the decrease in temperature is resisted by undergoing the exothermic back reaction, which will heat up the system. Then, what if the forward reaction is exothermic? Well, the same sort of thing. If we heat it, wait, that's the snowflake. If we heat it, it'll undergo the back reaction, which is endothermic, to take in the energy. And if we cool it, it'll undergo the forwards reaction, which increases the temperature. So it always comes back to resisting that change. Resisting it, not negating it. So if I were to, like, I don't know, add 100 kilojoules through my plasma syringe, that doesn't exist, but let's just say it does. this exothermic reaction, the back reaction will occur, but it'll only eat about I can't give you an exact number, but we'll just say 60 kilojoules it eats up. So it's not completely opposed, it's just partially. It can't completely negate it. Alright, now equilibrium in industry, it's a very big thing. Like, whenever you want to produce any sorts of chemicals, you have to worry a lot about equilibria. Clashes come, however, when you think about, do I want to use temperature to increase the extent of my exothermic reaction, or increase the rate of reaction? Because if you heat up an exothermic reaction, the extent of the reaction slides to the left. To the left? To the left. And it does make KFC lower. It's the only factor that can do that. Which I should have mentioned earlier, sorry. Heat, temperature, directly influences the equilibrium constant, the equilibrium quotient. And it's the only thing that can do that, other than the coefficients and the order of the reaction. But it creates conflict in industry. Do you want to have a reaction occur at an extremely fast rate, or do you want to have a really product biased reaction? If it's an endothermic, that's great. You can heat it up, and it also increases the extent of reaction. But if it is exothermic, that's something that we have to keep, in the back of our minds always. Usually, they'll come to a compromise where it's not freezing cold, but it's not making the reaction unfeasible, yielding not enough. And usually there's workarounds. Now, industry adores catalysts because they're not consumed in the reaction. They increase the reaction rate sometimes like exponentially. And, well, they're not always cheap, but they can be cheap. Now, one of the best examples of equilibrium is in our body. We have hemoglobin and competing equilibria. This is the body cells, no, not the cells, this is hemoglobin molecules in someone who was just in a fire, in a house fire. So they've inhaled a lot of carbon monoxide made through incomplete combustion of most things. And it's binding heavily to this hemoglobin protein. It's important to be noted, carbon monoxide bonds extremely strongly to hemoglobin. Much, much, much stronger than oxygen. Which is to say, the KFC for carboxyhemoglobin is higher than that of oxyhemoglobin. We do attempt to treat people who have carbon monoxide inhalation by adding lots and lots and lots of oxygen, pure pressurized oxygen. This is to try and elicit a change from Le Chatelier's principle that the increase in oxygen is opposed by forming more oxyl hemoglobin. Though, unfortunately, considering just how much higher carbon monoxide's KFC is, sometimes it's not enough, and especially if a person has been in a house fire for a while, if you've got all of these carboxyhemoglobin complexes, they're not getting enough oxygen, they do get brain damage or die, just because they don't get it in time. But if they do, this is the best medicine. Alright, now for what a lot of people didn't appreciate as much on the last test. Okay, electrolysis. Electrolysis is defined as the applied current to drive a non-spontaneous reaction. I'll just explain this a bit better. It's when you put electricity through things, when you force a current through a system, that doesn't want to happen. So it's not like a galvanic cell where you attach it and it's eager, it wants to get going, and it does it on its own and it makes electricity. It's the opposite. You have to really hammer it into it to make the reaction occur, which we call non-spontaneous. One of the most important things is predicting the products of electrolysis. In any aqueous or molten cell, we use some rules to determine the products in a reaction. Now, Miss says something with the backwards Z or I don't know how that works. I just sort of, like read the data book and get it from that. But if that works for you, go ahead. But first, of course, you have to determine the present species, split them up into different oxidant or reductants, and then find the strongest oxidant and the strongest reductant. Now, it's not that hard when you break it down, and once you do a lot of practice questions, but the first time it can be fairly daunting. So I'll go through an example. Determine the oxidant and reductant in the following cell. So in this cell, we have a magnesium cathode, a copper anode, and a lithium chloride solution. Everything's at 1 mole per liter, it's at 25 degrees and at 1 atmosphere, which is standard conditions. So we can use the data book for a one-to-one prediction. So let me just... Okay. So looking at all the species we have in this reaction, there is magnesium. I'll go from top to bottom. So we have chlorine. We don't have chlorine gas, but I'll just write all the reduction equations. We have water, which is we have copper, we have water again, sorry for the bad handwriting, and finally we have lithium. You might be asking, why is magnesium in this? Seeing as magnesium is connected to the cathode, it is receiving a constant, undying supply of electrons. So it's always pumped full of them, so it can't be oxidized. It's inert. Like you could have I wouldn't do it, but you could have a rod of lithium, and if the current supplied, it wouldn't react, even though it usually reacts vigorously with water. So let's look at what we have here. We have chlorine, we have water, we have copper solid, we have water, and we have lithium ions. Now, candidates for reduction. We have lithium and we have water. All of these are in their reduced state, so they can't be reduced. Now, water is higher on the electrochemical series, so water will be being reduced in this cell. So H2OL plus 2E minus goes into H2 gas plus 2OH minus AQ. And then we look at what else we have. So we can ignore these now. We have copper solid, we have water, and we have chlorine. Now this is looking for the strongest reductant. or what is most eager to give up its electrons. Copper is the lowest on the electrochemical series out of all of these, so copper will be oxidized. Another important thing to know how to do is to find the voltage. So we have E of O equals, is this 2, negative 0.83, and E of O equals 0.15. It's always the oxidant minus the reductant, so you have minus 0.83 minus 0.15 gives us negative 9.98 volts. But it asks us to determine the voltage required to drive the cell. Well, you can't drive a cell with negative voltage, so it's positive 0.98 volts. It's important to note here, even though we have an electrolyte, none of the electrolyte reacted. It can be things that really take you off guard. So don't be surprised if there's like, I don't know, an iron coating. Actually, no, that doesn't make sense, sorry. But just make sure to thoroughly list everything present in these cells. A big part of this is comparing galvanic cells and electrolytic cells. A galvanic cell separates reactants, as they can react spontaneously. The electrolyte separates products, because they're the ones that react spontaneously. Galvanic cell has chemical to electric. An electrolytic cell has electric to chemical. The anode is negative in a galvanic cell, where it's positive in a... No, sorry. The anode is negative in a galvanic cell, where it's positive in an electrolytic cell. The cathode is positive in a galvanic cell, when it's negative in an electrolytic cell. Alright, industry and electrolysis. In industry, electrolysis is the most feasible way to produce many metals and gases. Some factors chemists consider is whether or not it can take place in an aqueous environment, do the electrodes have to be replaced, and can we use catalysts? Obviously, we always want it to occur in an aqueous environment because it's so much cheaper than constantly having something heated to the point where it's molten. Do the electrodes need to be replaced? That's also a really big bother, as you have to not only replace the electrodes, you have to, stop everything, pull it out. Eventually it'll degrade over time, which lowers the efficiency of the cell. And can we use catalysts? We're always after trying to use catalysts because it just increases the reaction rates with no downsides apart from maybe buying it. Alright, and here we have a membrane cell. While it says we don't need to know any specific ones, Mrs. She recommends it a lot that we have a look at them. So, it can't hurt. This membrane cell is what we use to produce sodium hydroxide and chlorine gas, as well as a bit of hydrogen. So what happens is a solution of what we call brine, which is very concentrated table salt, is put into a cell. It's electrolyzed, so the chloride ions are stripped of their electrons, becomes chlorine gas that goes out. The sodium can pass right through it. So as the sodium passes through it, it gets pumped out through here. Because this is an aqueous environment, the water is being reduced. So it's all water. And the water gets reduced, producing hydrogen gas, which goes out. So we're left with sodium and hydroxide ions. Sodium hydroxide is fairly useful in a few things, so we like to get that out as well. Another kind of cell that's not used today is called a diaphragm cell. It's essentially the same thing, but instead of this nice membrane we have here, it was an asbestos layer. The asbestos layer wasn't as good of a net, so this was a bit less pure. Also, we don't really like using asbestos for a lot of things. It's a bit of a potent carcinogen, so yeah, we try and avoid using it. But here's a nice and icky version of a whole Herald cell, which is what we use to reduce and extract aluminium. So it's a pretty interesting cell, personally, because instead of taking place in an aqueous environment, it takes place in an environment of molten ionic compound. This ionic compound is cryolite, and the alumina is actually dissolved in an ionic compound, obviously as a liquid. That's not important at all, but I just think it's a bit interesting. So yeah, this is just essentially an industrial version of a cell. We don't need to know a lot about it. You should know alumina has this formula, and we don't like the oxygen. Oxygens are very annoying to deal with, so that's why the cathode has to be made out of graphite. Because the graphite, the carbon, reacts with the oxygen to form CO2, and eventually over time the cathode does degrade and it has to be replaced. Research is being put into finding a different kind of electrode that doesn't have to be replaced, so we can improve the efficiency of aluminium production. Okay, now onto the nice stuff. Faraday's laws. Faraday's first law states, as more charge flows through a cell, more metal is reduced, which essentially says Q is directly proportionate to mass, where Q is of course charge. The second law is that it takes about... Hold a second, I don't think that's right, is it? Where is it? 9650. Yeah, this one's wrong, sorry. So it takes about 96,500 coulombs to reduce 1 mole of X plus ions, where X plus is any ion with just a +1 charge. So the coulomb is a bit of a tough thing to understand, but it's a international unit of measure for electric charge. You can think about it as the amount of electricity. Its symbol is Q, and we of course measure it in coulombs. We find it by multiplying I, which is amps, and T, which is time, in seconds. So if you get like 5 minutes, you have to do 5 times 60, find 300 seconds, and then use that in your calculations. The Faraday is a bit annoying too. The Faraday is defined as the charge of 1 mole of electrons. It is equal to 96,500 coulombs. So I'll just say it again. It is the charge of 1 mole of electrons. So 1 Faraday is 1 mole of electrons. There may very well be a question where it's something like this. And it asks how many Faradays are needed to reduce 1 mole of this. So we have 1 mole, and we want to find it. We want to find how many electrons it takes. So this is a 2. What you want over what you got. So it equals 2 mole. And it's asking how many Faraday. Well, 1 Faraday is the charge of 1 mole of electrons. So we have 2 moles of electrons, so we have 2 Faradays. Another way to define it is a Faraday can reduce 1 mole of X+, where X+ is an ion with a charge of +1. Now, being able to dance around from coulombs to grams to grams to coulombs to grams to time to whatever is probably going to be very important on this sec. So, you have to remember this whole chain. It's a bit annoying, but it is very helpful. So, if we have I and T, or amps and time, we get Q, we divide Q by Faraday, it gives us the number of electrons. We look at the equation, so X plus charge, we need X electrons to reduce it. So we divide the number of electrons by the charge to find number of X. Then we times the amount of X by X's molar mass to find the amount of X, to find the mass of X. Yeah, if you don't know how to do this, you're going to have a pretty rough time on the sec, I'm going to think. And to end it off is something that I'm not even sure will be on the sec, is secondary cells. A secondary cell is a cell that can be recharged. It acts as a galvanic cell as it discharges and an electrolytic cell as it recharges. Its cathode and anode switch when recharged, which is to say, what was once the side of reduction is now the side of oxidation. And the side of oxidation is the side of reduction. It's important to note as well, the poles don't flip, only cathode and anode. So that's why the cathode's negative and then the anode's positive. A few things we need to know about secondary cells is how they degrade over time. Obviously, it's not a perfect system, a battery. As you shake it around, as you get it wet, as you just leave it on a table, side reactions occur, which is when, reactions just, they sort of happen and there's nothing you can do about it. And, it might distance some reactants from an electrode so it can't be reduced or oxidized anymore. Or it might damage the casing and let the electrolyte leak. Any sort of fault you can think of, it can probably happen. Again, I'm not sure if secondary cells are going to be on the test. I think we covered that in area of study 1. But just a heads up, this might be mean. Okay. That should be everything. I hope you enjoyed. If you watched, I'll see you tomorrow. And good luck on the set.